welcome to the second video for lesson 4.4. We're still talking about bivariate distributions of the continuous type. In this video, we will look at marginal distributions and their expected values, and conditional distributions and their expected values. We're going to be working with this example. We have a joint PDF of the random variables x and y, given by f of xy is equal to x squared plus 8/3 xy, and x can take on values between 0 and 1, and y can take on values between 0 and 1. And if we were to integrate over this sample space, and here's our sample space, this probability density function, that would integrate out to 1, so this is a valid probability density function. Let's start by defining marginal probability density functions. So rather than summing a discrete joint PMF, we are going to be integrating a continuous joint PDF. The marginal probability density functions can be used to make probability statements about one of the variables without thinking about the other variable at all. And the way we can define them is if the joint probability density function of variables x and y is little f of xy, then the marginal probability density functions of x and y can be defined as f sub x, which is our marginal distribution of x, is equal to our joint PMF, f of xy, integrated with respect to y over all of the possible values that y can take on. And similarly, our marginal PDF, f sub y, which is our marginal distribution of y, can be found by integrating the joint PDF at little f of xy with respect to x over all of the possible values that x can take on. So let's take a look at our example. Got our margin, we're going to calculate our marginal PDFs. For our marginal PDF with respect of x, our marginal distribution of x, we're going to find by integrating over all the possible values of y, so that's from 0 to 1, our PDF, x squared plus 8/3 xy. And if we do this with respect to y, it gives us a marginal PDF of x equal to x squared plus 4/3 x, defined for values of x between 0 and 1. If we want to find the marginal distribution of y, we integrate over all the possible values of x. So x can go from 0 to 1, so those are our limits. We take our joint PDF, x squared plus 8/3 xy, and this gives us a marginal distribution of y equal to 4y plus 1 over 3, defined for values of y between 0 and 1. Those are our marginal PDFs. Now, if we want to find the mean and the variance of the marginal distribution, we're going to take the expected value of x, that's going to be our mean of the marginal distribution of x. We can do this one of two ways. We can either integrate with respect to x and y over the entire sample space and take x times f of xy. Or we can integrate just with respect to x over all of the possible values of x, and we can take x times the marginal distribution, f sub x. The same is true for the variance. We can do it one of two ways. We can either integrate over the entire sample space, x minus mu sub x squared times our PDF, or we can take x minus the mean of x squared and then multiply by our marginal distribution and integrate with respect to x over all the values that x can take on. So you can do this either way. They'll give us the same answer. And we can still use the fact that the expected value of x minus mu sub x squared is equal to the expected value of x squared minus mu sub x squared, to use sort of the shortcut formulas that we've used all along. These things can be defined completely analogously for y. I'm not going to go through the separate definitions for them. So let's look at our example again, and we'll find the mean of the marginal distribution of x and the variance of that marginal distribution of x. If we want to find the mean of the marginal distribution of x, we're going to integrate over all the values of x from 0 to 1, x times our marginal distribution of x. So I'm integrating from 0 to 1, x cubed plus 4/3 x squared dx. And that gives me a mean of that marginal distribution of x, mu sub x, equal to 25 over 36. I can also find the variance. I'm going to use my shortcut formula. I'm going to find the expected value of x squared and then subtract that mean 25 over 36 that I just found squared. To find the expected value of x squared, I integrate over all the possible values of x squared times the marginal distribution of x, dx, which gives me 8/15. 8/15 minus 25 over 36 squared gives me a variance of that marginal distribution of x of 0.0511. Now our conditional probability density functions, the definitions look exactly the same as they did in the discrete case. If I want to find the conditional distribution of x given y, g of x given y, I take my probability density function, f of xy, divide it by my marginal distribution of y, and use that to find my conditional distribution of x given y. Can do the same thing to find the conditional distribution of y given x. That's my h of y given x. I take my joint PDF, f of xy, divided by my marginal distribution of x, and that gives me my conditional distribution. Now I can also define the mean and variance of my conditional random variables. I can find the mean of y given x by integrating over all the values of y times my conditional distribution of y given x. And I can find my conditional variance by integrating over all of my values of y minus the mean of y given x squared times my conditional distribution of y given x. Or I can use the shortcut formula. Coming back to my example, here's my conditional distribution of y given x. If I want to find my mean of y given x, I'm going to integrate over all the possible values of y times my conditional distribution of y given x. And this gives me my mean of my conditional distribution of y given x is going to be 9x plus 16 over 18x plus 24. And so this is going to depend on x. Similarly, I could find the mean of x given y by integrating over all the possible values of x times my conditional distribution, g of x given y. And that gives me the mean of x given y equal to 9 plus 32y over 12 plus 48y. We can also find the variance of the conditional distribution of y given x by taking the expected value of y squared given x minus that mean of the conditional distribution, which we just found. My dogs are noisy today. I'm going to start by finding the expected value of y squared given x, which is equal to x plus 2 over 3x plus 4. Then I take that expected value of y squared given x and subtract off my mean squared. And it gives me my variance. I might be able to simplify that formula, but basically there it is. So that brings us to the end of our second video. In our third video for lesson 4.4, I am going to look at calculating covariance, correlation, and also the least squares regression line when we're working with continuous bivariate distributions.